Okay, good morning, everybody. It's my pleasure to introduce Dr. Matteo Tacca, and I'll give you a little bit of background. After getting his master's and PhD degrees in information technology and optics, he joined the gravitational wave community and spent 3 years at the Virgo site in Italy, directly working with the Virgo interferometer. And Matteo then moved to the laboratory astroparticle at cosmology in Paris, I probably butchered that, in order to assemble and test some optical systems installed in advanced Virgo, which is the second generation detector, an upgrade of the Virgo. The next he moved to NIKHEF, NIKHEF, the Institute of Subatomic Physics in the Netherlands, and continued to work on other topics of advanced Virgo detector. And he's been working with both American LIGO and the Japanese KGRA experiments, and since July of 2019 has been in charge of the coordination of the commissioning activities of advanced Virgo, both during the 03 observation run and during the upgrades planned before the 04 observation run. So I'll turn the meeting over to Dr. Tacca, and please to hear your talk.
So thank you, Tom. First of all, I would like to thank you for inviting me, for giving this this talk. It's a great pleasure for me. So from now on, I will stop my camera and I will share my screen. As you said, I am basically, well, with a background on the instrumentation part of this very nice, I would say, field of science. And well, I will try to talk about how a ground-based gravitational wave detector is working, and I will try to present the results that we obtained during the last observation run that was last year. So let me start first giving some reminds about general relativity and gravitational waves. As you know, in 1915, Einstein wrote about, for the first time, the general relativity, his theory of general relativity, introducing the dynamic space-time, and in particular, he also introduced the gravity as the curvature of the space-time. And 1 year later, he introduced also the concept of gravitational waves that are ripples in space-time propagating at the speed of light. It means that if there are large masses, they can perturb the space-time and creating these ripples that can propagate. And exactly 100 years later, then the introduction of the general relativity, the gravitational waves were observed directly for the first time. As you know, there was this huge event on 2015. In particular, there was this very loud signal detected by the two American interferometer LIGO at Hanford and Livingston that well, gave born to this new, I would say, astronomy, the gravitational wave astronomy. And indeed, at that time, the two interferometers were able to detect the merger of two black holes, binary black holes, one characterized by 36 solar masses, and the second one characterized by 29 solar masses, for a total solar masses of 62 for the let's say, for the final black hole that was generated at the end of the merger. And it means that 3 solar masses were in some sense lost in gravitational waves. And this was that at that time, so 5 years ago, this was the brighter event that was ever detected in the entire universe. So that was amazing for us, obviously, and that was also surprising for us in the sense that we didn't expect to detect a gravitational waves from such a loud event and so early, already in 2015. So we were lucky, but we were really, really happy about that. So, but let me just tell you what we have to do in order to measure gravitational waves. So just a reminder, what happens if a gravitational wave is arriving on Earth? A gravitational wave basically modifies the distances. In particular, it can stretch the space in one direction and compress the space in the other direction. But the deformation that is introduced by the gravitational wave is really tiny. It is of the order of 10 to minus 18 meters. But what does it mean, 10 to the minus 18 meters? Well, it's 1,000 smaller than the size of the radius of a proton in one atom. So it's really something that is, well, at least for me, that I'm working on this business, it's something that is really difficult to understand, to imagine. So I would like to tell you how we can measure this tiny deformation. So we use a very, let me say, simple concept, something that is quite standard in optics and in measurements, that is a Michelson interferometer. And how does it work? So we have a laser source. I don't know if you can, okay. We have a laser source that is divided into different beams by a beam splitter. These two different beams can propagate along two perpendicular paths. At the end of this path, there are two mirrors that reflected back the two original beams, and the two beams are then recombined at the level of the beam splitter where they were divided at the beginning. And what we measure the light at the output of this system, and we can decide to tune our interferometer mainly in two different working points. The first one, that is actually what we use, is the dark fringe working point. That means that we are trying to make a destructive field at the recombination of the two beams. And the other possibility is to tune the interferometer in the so-called bright fringe, where we have a constructive interference. But as I said, we would like to have a destructive interference. And what happens when the gravitational wave is passing through the interferometer? Well, the gravitational wave is perturbing and is changing the working point of the interferometer, so that the light that is acquired on the photodiode is changing, is slightly changing. So, but as you know, the first probably know, the first interferometer was made by Michelson and Morley many years ago. But what was the smaller quantity that they can measure at that time? So they can measure something of the order of lambda over 50. And today we have to move to measure something of the order of, as I said before, 10 to minus 18 meters. That is lambda over 10 to 12. Considering that we are using a laser beam that has a wavelength of about 1 micron. So how can we do this kind of measurement using a Michelson interferometer? So as I said, this is just a small movie that is showing you what is happening with the gravitational wave is passing. So as you can see, the space is stretched in one direction and compressed in the other one. And at the output of our interferometer, the photodetector is changing the amount of light that is acquiring, passing through no signal up to having some signal, and so on. So we are using exactly this trick. Obviously, in this animation, it is exaggerated a bit. The amount of light that we can measure is very, very low, but this is the main concept. But as I said, we had to introduce some tricks in a simple Michelson interferometer in order to be able to measure such a tiny deformation. In particular, we needed to add some additional components. So instead of having two mirrors at the end of the path of the two beams, of the two laser beams, we introduced two cavities. That is just to mimic a longer path made by the two beams. And in particular, I can tell you that we are using two Fabry-Perot cavities as arms of the interferometer. And for the Virgo case, that is the European interferometer, the two Fabry-Perot cavities are long 3 kilometers, while for the LIGO interferometers, these cavities are long 4 kilometers. But it is not enough. So we introduce, as I said, these cavities in order to increase the amount of light that is going back and forth in our experiment. But it is not enough. As I said before, we would like to tune the interferometer in order to have such a destructive interference at the output. It means that most of the light is going back towards the laser source. So we decided to install another mirror between the laser source and the beam splitter in order to be able to re-inject the laser light that is lost tuning the interferometer in dark fringe working point. We call this mirror a power recycling mirror, and as the name is explaining, it is used to recycle the power that would be lost in different cases, and this power is this light is re-injected inside the experiment. And right now we are also installing another mirror at the output of our system. We call this mirror signal recycling mirror, and this is used to change the shape of the bandwidth of the sensitivity of the detector. This is, in this scheme, I'm just showing you the basic concept of these detectors. In particular, this is the scheme of Virgo, but also the scheme of LIGO and Kagra. Kagra is the Japanese detector. They are conceptually the same in the sense that there are the same elements that have been added. But this is only the first point, in the sense that our experiment is not made only by these, let's say, for 8, 9 mirrors and few components. We need also many other optical components in order to be able to shape the beam and to adapt the beam to our experiment. And in particular, we have a system that we call input optics system that is used to modify the laser beam that is coming out from the laser source, and to adapt this beam to the entire experiment. Just to give you an example, a standard laser beam that is coming out from a laser source can have a radius of about 1 millimeter, while inside our experiment we have a beam that is resonating that has a radius of 5 centimeters. So we have to clearly increase at least the size of the beam, and also we have to change other properties of the input beam. And at the output, we have another system that we call output optics system that is used on the other way around. It means that this system of optical components is acquiring the beam coming from the interferometer and is reshaping this beam in order to be detected on a photodiode. But it is not enough, in the sense that we have here and then there are some other optical benches with other optical components and electronics in order to be able to control the whole experiment. It's just to say that it is not, even if the conceptual scheme of the experiment is very simple, such as a microson interferometer. In practice, it is really complex to be realized and implemented. And just to summarize, so we have this interferometer that is based on the ground, and we would like to measure the fluctuation that are induced on the mirror, on the arms of the interferometer. But these mirrors can be moved also by many other phenomena. For instance, they can move by the motion of the Earth. And we call this motion such as seismic noise. It means that obviously the Earth is moving. We have not only earthquake, but also we have any kind of motion that can perturb the status of the mirror inside our experiment. Then on the mirror itself, we can have the motion of the molecules that are making, that are composing the substrates and the coating of the mirror. This is the Brownian motion of the molecules, and we call this perturbation as a thermal noise. And then also we have another kind of noise that is related to the fact that we are using laser beam, and the laser light can be considered also as quantum element. So the light is made by photons. So how this amount of photon are hitting against the mirrors or are detected by the photodiode will perturb the experiment itself, and we call this kind of perturbation quantum noise. And then we have also other noises that we call the technical noises. It means that they are mainly related to the technology that we are using to build our experiment. And in particular, we have the instability of the laser source. We need a very, very stable laser. And we have also some defects on the optic that we are using. And these defects are scattering the light that is impinging on the optics here and there, creating scattered light. And then all the environmental conditions are introducing perturbation. And we call this as environmental noise. So going briefly on these noises, just I took the example, I'm working in Virgo, so I took the example of Virgo, but please consider that LIGO and Cagra are almost the same. So there are probably some technological solutions that are a bit different, but the main purpose is the same. And in particular, going back to the seismic noise, I can tell you that at the Virgo site, the seismic noise was measured using accelerometer and seismometer, and it is of the order of 10 to minus 9 meter. As I said, we would like to measure something of the order of 10 to minus 18. So we have to attenuate this motion that is induced by the Earth. So in order to do that, we suspended the mirror at the bottom of a very high chain of pendula. And in particular, this is there is the design and some pictures of the mirror of the Virgo suspension. As you can see, there are some filters that are filtering are filtering this residual motion of the Earth. And at the bottom, the mirror that is shown on the picture on the right is suspended. So this is one of the mirror that are installed in Virgo right now. This chain of pendula is able to attenuate the residual motion by something of the order of 10 to minus 10. It is allowing us to be able to measure gravitational waves. In Virgo and in Cagra, there are some passive systems, such the one that is shown here. The one in Cagra is very similar, while in LIGO there is a combination of active and passive system, in the sense that there are some pendula that are attenuating the motion, but there are also some actuators such as coils or other technical devices that are keeping the mirror as that are not keeping, that are reducing the motion of the mirror. Going on, I introduced before the thermal noise. What is the thermal noise? As I said, the thermal noise is the Brownian motion of the atoms that are composing the mirrors, but not only the mirrors, also the wires that are used to suspend these mirrors. So we have a different kind of thermal noise. The thermal noise can happen in the wires, as I said, and it is due to the losses, mechanical losses proper of these wires. And it can happen also on the mirror itself and on the coating of the mirror. And what I can say that in order to reduce the losses on the wires, in all our experiment, LIGO, Virgo, Cagra, we decided to suspend the mirror using glass wires. Our mirrors are made in silica, and we were able to find and to create also wires, suspension wires that are made in silica as well. And these wires are bonded and welded on the side of the mirror. You can see a picture of these wires on the left. And in this way, we are creating a monolithic structure between the mirror and the wires in order to reduce the residual motion due to the losses. On the left, sorry, on the right, there is a picture of a mirror. You can see this mirror that is pink, since on the surface of this mirror there is a protective film that is removed only when the mirror is installed. And the main losses are due to the defects that are on the surface of the mirror. As you can imagine, the ideal mirror is perfect. The surface is homogeneous in all over the area, but it is not possible from the technological point of view to have such an ideal mirror. So there are some defects, some points here and there on the surface of the mirror that are introducing losses and are creating of this also this residual motion. All the mirrors are coated with thin films that we call coating, that are produced in Europe in a French lab. All the mirrors for all the experiment, the Japanese, the American, and the European one. And these coatings are very nice, since the losses of this coating are very low. Let me say that right now, the losses of the coating of the mirror are still one of the main limitations for the sensitivity of advanced gravitational wave detectors. Then, as I said, we have the quantum noise. The quantum noise is related to the quantum nature of light. So, as I said before, the light is made by photon, and we have two different components of quantum noise. We have the shot noise that is limiting the sensitivity at high frequency, and the radiation pressure noise that is limiting the sensitivity at low frequency. And these two different noises, quantum noises, are the first one. The shot noise depends on the number of photons that are impinging on the photodetector, and this is going as 1 over the input power. It means that if we decide to increase the input power, so we have a much higher input power laser, we can decrease the impact of the shot noise. But we have a counteraction of increasing the input power, since at low frequency we have the radiation pressure noise that is depending on the input power itself. So if we increase the input power, we have an increase of the radiation pressure noise. What is the radiation pressure noise? The radiation pressure noise is the motion of the mirror that is induced by the photons that are impacting on the surface of the mirror itself, and they are moving slightly the mirror. But we have another trick to try to reduce the radiation pressure noise, since we know that this radiation pressure is depending on 1 over the mass of the mirror. So we are trying to increase also the mass of the mirror. And in particular, right now in LIGO Virgo, there are mirrors that has a mass of about 35 to 40 kilograms. And in the future, we are planning to have mirrors with mass of the order of 100 kilograms in order also to reduce the impact of the increasing of the laser power on the system. And then going towards what we call the technical noise, we can talk about the frequency noise. What is the frequency noise? So we need a laser light that is really stable. It means that the frequency, or if you would like to see at it as a wavelength, we need the wavelength of the laser that is really stable, and it is really the one that we decide. For instance, we are using a laser with a wavelength of 1064 nanometer, and we would like that this frequency is really 1064 nanometer. And if you buy the best laser that you can find on the market today, this laser has a residual frequency noise of the order of 10 to 4 over the frequency around 1 hertz, and we would like something of the order to 10 to -6. So how can we stabilize the laser? The frequency of the laser, we try to lock the frequency of the laser that we use on different auxiliary cavities and on the interferometer itself. It means that we have the length of the cavity, and we are using the length of the cavity as the reference to define the exact frequency of the laser that is injected inside the experiment. Here on this picture, I just show some optics and devices that are installed in one of our optical benches, just to show how complex it can be. And going on, one of our worst enemy is the scattered light. As I said before, it is almost impossible to have perfect mirrors, perfect optical devices, and it means that any kind of light that is impacting on our optics can be scattered here and there by the defects that are present on the surface of the optics. And it is impossible to predict it, and it is also very difficult to handle this problem. So we are trying to improve any time this mitigation, and we are trying to use different strategies. For instance, well, for sure at the beginning we started making simulation in order to understand how the scattered light can go. But then it is not enough. So we are building baffles that are sort of absorbing glasses. These are glasses that we put here and there in the experiment, and these are used to absorb the light that is scattered away from the mirrors, from the defects of the mirrors. And we are installing this kind of baffles along the pipe, around the mirrors, on the optical benches, everywhere, I would say. And moreover, there is another upgrade that we introduced, that is, we are suspending almost all the optical benches. It means that right now we have only the laser source that is on ground. All the other optical systems are suspended with a simplified system with respect to the one that we use for the main mirrors, but with a similar system, in order to decrease the motion, the residual motion of all the optics. In this way, the scattered light is not going around too much, and we try to keep all the optics in the good position. Last but not least, all these experiments are in vacuum, since also the perturbation introduced by the air can move the optics. So I can tell you that advanced LIGO, advanced Virgo are are characterized by a very large vacuum tank, and in particular, I think that Virgo is the largest vacuum environment in Europe, or the second one. I don't remember well if the first one is the LHC at CERN, or it is Virgo, but just to say that in order to handle this experiment, we also need very large vacuum environment, and the residual pressure is very low. In the pipe of LIGO Virgo, the residual pressure is of the order of 10 to minus 9 millibar for the hydrogen. So going on, just to let you know where these gravitational waves are based. So as I said before, right now we have two LIGO interferometer in US, one in Louisiana near Livingston, and the other one in Washington State in near Hanford. There is the European one, Virgo, that is in Italy. And then there is another European interferometer that is called Geo 600, that is interferometer with the arms that are 600 meter long. It was used in the past. It is always online with us when we acquire data, but it is also used as a test bench for new technologies that should be tested before the installation in the kilometer scale interferometer. Now we have also Kagra that is in Japan, and Kagra is a particular interferometer since it is already introducing two upgrades that we are planning for the future. It means that Kagra is built underground, it is inside the mountain, and it is working with a mirror at cryogenic temperature. These two upgrades, I mean, having an interferometer underground and working at cryogenic temperature, are two upgrades that we cannot implement right now in LIGO and in Virgo, but they are foreseen for the third generation of detector that will be built in 10 to 15 years from now. And in the next 4 to 5 years, we will have also another LIGO interferometer that is a copy of the two LIGO interferometers, and it will be built in India. It was approved, and they are already working on the site in order to acquire the land and to start to implement the infrastructure. So just to say that gravitational wave detector can work very well, making all the science that we are trying to do only if they work as a network. So the importance of having all the interferometer working at the same time is huge in order to have very nice results, in order to have very spectacular science results. I will try to explain it later on. So what happened right now? So the network, as I said, is based today by these 5 interferometers, the 2 LIGOs, Virgo and Geo and Kagra. But in the future, there will be also another LIGO. And our experiments are working together. It means that there is an agreement between LIGO and Virgo since 2007. And thanks to this agreement, we are sharing technologies, we are sharing data, we are making common analysis on the data, we are publishing results together. This is the only way to be good in the science that we are trying to do. And last year, yeah, I would say November last year, if I remember well, also an agreement with Kagra was signed, and in the future we will have common data among LIGO, Virgo, and Kagra, and common analysis and common technologies in order to improve the capacity and the performances of the global network. What are the plans? What were the plans, and what are the plans right now? So, as you know, probably the first detector was made during what we call the first observing run 01 that was made in 2015, in particular from September 2015 up to January 2016, and we had only 2 LIGOs detector at that time. Then we had the so-called O2 that started in 2016, November 2016, and last up to August 2017. And Virgo joined this second observing run for the last month of data, data taking. And let me say that it was impressive how the rate of event that we detected increased as soon as we had the third detector in the network. And then we had O3 that lasted from April 2019 and should have lasted up to and the end of April 2020. And the initial planning was that Kagra would have joined the run towards the end for the last couple of months. But as you know, we had some problem with the pandemic, but I will talk you in a while about that. So this is just a summary on what was detected during O1 and O2. We had 11 confirmed detection of gravitational waves, and in particular, we had 10 of them that were gravitational wave emitted by the merging of 2 black holes, and one of them in this plot is the bottom right figure, was the famous, I would say, detection of gravitational wave emitted by the coalescence of 2 neutron stars, and that was a really amazing event, completely unexpected by us. And I remember that day. That was the day when we really started the multi-messenger astronomy together with all the other kind of detectors for electromagnetic and optics and gamma ray, etc., detectors and telescopes that are all around the world and in space. So but just to say that in the first 2 runs, we were able to detect 11 gravitational waves, and then we can come to O3, that is the last observing run. As I said, the original planning was to have 12 months of data, with a break in after 6 months in order to update and upgrade a bit the machine, the interferometers. So we would like to acquire data continuously for 6 months, then stop for 1 month in order to make some commission and upgrade on the machine, and then run for other 6 months in acquiring data. But what happened? As I said, it happened that the COVID-19 pandemic arrived, so we had to stop the observation 1 month before. So we ended O3 at the end of March 2020 instead of at the end of April. And Kagra was not able to join since they were very close to the target sensitivity, but not yet there. So that was a pity for us. All the activities were suspended, and after a long discussion, we decided to focus both LIGO, Virgo, and Kagra on the upgrades in order to improve the machine for the 4th observing run. In spring, there were, in any case, 2 weeks of what we call the Astrowatch. That was a joint data taking between GEO and Kagra with very low sensitivity, but it was used at least to test how Kagra works and how they are able to acquire data, to share data, and in order to be ready for the next observing run. And now just some results about that. This is an image of the O3 duty factor, that it was very good. The whole period was of about 183 days, and we had a very, very small downtime. It means that only the 3.2% of time we didn't have any of the 3 detector online. That is, it was very good for us. It means that for most of the time we had at least 2 detector, 1 or 2 detector online that that was there to see if there were some gravitational wave arriving on Earth. This is the duty factor of O3b, that is the second part of the run O3. As I said, it was slightly shorter, and also for that we had 85% of duty cycle with at least 2 detectors online. And also for this second part of the run, we had a very small amount of time with no detectors online, only 3.5%. And just let me say that on purpose, we decided to decrease a bit the duty cycle of Virgo for this second part of the run, since we wanted to boost a little bit our sensitivity in order to reach our target that was of about 60 megaparsec. And these are the performances of the detectors, the 3 detectors in the 2 parts of the O3 run, O3A and O3B. As you can see in both of them, LIGO Livingstone was the one with the highest sensitivity. That is the one that is characterized by the blue curve in these plots. Then there was LIGO Hanford that has a sensitivity that was slightly worse. And then there was the Virgo detector that has a sensitivity that was more or less half of the one of the LIGO. But let me say that it was already in the plan to have such difference in the sensitivity, in the sense that LIGO started operation 2 years before Virgo. So we have also about 2 years in gaining the sensitivity and the amount of megaparsec that we can scan. And this is the main results. What was impressive, as I said before, in the first 2 run, O1 and O2, we had 11 gravitational wave signals detected by our experiment. And in O3A and O3B, we had 80 gravitational wave only candidates. It means, as you can see on this plot, the rate of events increased tremendously during this third observing run. After some study of this event, we had 24 retraction, but at the end of the run, we had 56 gravitational wave candidates that can be signal emitted by really gravitational, let's say, astronomical event that can emit gravitational wave. And we are talking about just the first online data analysis. You can imagine that this amount of event can increase during that offline data analysis that is still in progress right now. So it was really amazing what we were able to detect so far. I would like to talk about you some particular events that we detect during the O3A period of O3. And let me specify that I will show you only O3A, I would say, since we are still analyzing the data of O3B. So far we focused our data analysis on O3A, and I can tell you about some of the events that we were able to detect in these 6 months of data taking. In particular, on April last year, we had the observation of a binary black hole coalescence with asymmetric masses. As you can see this in this slide, this was a first observation of a binary black hole merger with that was made by 2 black holes that were very different. One of the 2 has 30 solar masses, while the other one was much smaller, of about only 8 solar masses. And that was the first observation ever of gravitational wave with high multipoles, and it can be very interesting, since all the information that were behind this observation can be used in order to understand further information of the sources of this event or to make some new test of the general relativities. So that was important for us, and not only for us, but for all the astronomical, astrophysical community, since this detection will likely improve the knowledge on the population of black holes that are in the universe. Then the second particular event we detect, it was still in April last year, and it was the observation of a compact binary coalescence with a total masses of about 3.4 solar masses. It was most likely a second binary neutron star merger after the famous 170817. And the analysis told us that indeed it is most likely a second binary neutron star, since it cannot be a binary black hole. The mass, the total mass is too small, or it cannot be also a merger between a neutron star and a black hole from the analysis and the theory and the model that we made. What is important to say? It is important to say that unfortunately we didn't have any electromagnetic counterpart for two reasons. The first one is that this this gravitational wave was very, very distant, much more distant with respect to the first one detected in 2017. And it was less well localized. And why it was less well localized? Since it was a two interferometer detection. It means that only Livingston and Virgo were online at that time. And it is stressing even more why all the network is really important, since with only two detectors, we are not able to really well localize the event, well, I mean, the region of the universe where the event happened. And in order to be very precise in the localization, in order to help the electromagnetic telescopes and detector to point in that direction, we would need all the detectors online. And why this was important? It was important also for another reason. That's the total mass was the larger one that was ever detected for any known system. I mean, if we don't know what is the outcome of this merger of two neutron stars, but what we know is this total mass of 3.4 solar masses is larger than any other system that was detected so far. So our open question is, can this event be an hint of new population of new objects in the universe? And we don't have right now the answer. Then in August, we had a detection of a gravitational wave from the coalescence of a black hole, that was sure, with a 2.6 solar mass. That was, we don't know yet what was that. In the sense that this coalescence was between a black hole of 23 solar masses, and we are sure about this black hole, while the second element of this merging could be either the lightest black hole ever observed or the heaviest neutron star ever observed, since 2.6 solar masses was so far never observed for both for neutron star or black hole. Another important property of this detection was that the mass ratio was 9:1, in the sense that one of the two objects was very, very larger than, or much larger, very much larger than the other. And many astrophysical implications could be studied thanks to this detection. And also new model to improve, not new model, but also the improvement on some model could be done. And then there was also another interesting event that was detected in May, and that was the binary black hole merger with a total mass of 150 solar masses. So right now, so far, I discussed about the lightest ever probably black hole in the previous event, while in this one, it is the most massive black hole ever detected through gravitational wave. And it was very interesting since the range of the masses of this black hole was never detected before. And it is, I would say, one of the final demonstration of intermediate mass black hole. As you know, the Nobel Prize of this year was given to people that studied in the past intermediate mass black holes, and that was another demonstration of intermediate mass black hole. And it was very interesting also since it can be used to trigger the study of the origin of the supermassive black hole that was never done before. So it was another important event with many astrophysical important properties. Then the last publication that we did, it was submitted to the journal, but it is public on arXiv, and also some seminar were already given in the last weeks, was the new catalog of the event that we detected as gravitational wave. In this plot, I just show you the huge amount of event that we were able to detect, considering only O3A, O1, and O2 observing grounds. You can imagine what can happen, including also the new analysis for the O3B observing ground, and what can happen in the future, improving the sensitivity of our detectors. So we are really opening a new era in the, I would say, in the astronomy, but we are at the beginning, and we really don't know everything on what we are detecting and what we are discovering right now. I would like just to give you some other information. So as I said, more to come. So another catalog will be published in a few months from now, including also the detection that we made during O3B. And if we have other special important individual events, we will make other particular publications with all the papers that are made together with the most important one, that are companion paper describing the astrophysical implications, such as the new estimation of Hubble constant, or testing of general relativity, etc. But as I said before, we still didn't finish the analysis, so we can find even more events in the data that we acquired so far. There is another interesting thing that I can tell you, that is LIGO and Virgo data after a while become public, but in particular, a very small batch of data around some particular publication is public as soon as the related paper of this event is published. So you can find public data about the single event that I described so far. And then we will make public some chunks of 6 months of data after 18 months after the end of the data taking. It means that we stopped data taking in spring this year, and the first 6 months of data, the data will be public in fall next year. And why that? For two reasons. Well, we need some months in order to be able to analyze the data properly, to give to make good science, and to have very demonstrated publications about events. And later on, all this data is good that become public, so that also other people can look inside them. And this is the link to the website with all the information about the public data and where you can find the data, where you can have all the all the information I said before. Now, a few words about the future. I'm running at the end of my talk. So, as I said before, right now we are focusing on the upgrades of the current detectors in order to have the so-called advanced plus detector. And we would like to have 4 detectors online for the O4 observing data. The O4 observing data at the beginning, I mean, few months ago, it was planned to start in January 2022, but it is not no more like that. It is not more real that since the impact of COVID was very strong also on our activities, both for people and for the upgrades that we have to install. So right now, the the impact of COVID is not yet clear for us. What I can say is that most likely O4 will not start before summer 2022. So as I said, right now we are installing some upgrades, and then we have to look for the proper working point of our machines, and then we can go online and acquire data.
Could you mention briefly the megaparsec numbers?
Yes, yes, yes.
Yeah. Okay.
I'm going on that. So in particular, for advanced Virgo, I can tell you that we have, as I said, this advanced Virgo Plus, that is a 2-phase project. The first phase that we call phase 1, and is aimed to, as O4 as a target, we are installing what I said at the beginning, the signal recycling mirror that was not installed so far in Virgo, but only in LIGO. We are increasing the input power up to 40 watts, and we are installing a new technology in order to reduce the quantum noise in all the bandwidth that is called frequency-dependent squeezing. And we would like also to cancel the so-called Newtonian noise, that is a sort of residual noise at low frequency. And the target for this is O4, while the target for O5 is the phase 2 advanced Virgo Plus. So we would like to further increase the laser power, and we would like to increase the mirror. So we would like to have larger test masses in order to have larger beam inside the cavities, and also heaviest masses, heaviest mirror. And we would like also to have better coding. And this is our target. So in this plot, you can see the real sensitivity that we were able to achieve in Virgo during O3A, the red one, and O3B, the blue one, with respectively 51 and 60 megaparsec, while for O4, we would like to have a sensitivity between 90 and 115 megaparsec, depending on how good we are in tuning the interferometer and how good we are in implementing the upgrades. While for O5, we would like to have a sensitivity that is in between 150 and 250 megaparsec. And this is just for Virgo. As you can see in this plot, the shape of the sensitivity will change, and the change of shape above 300 Hz is due to the installation to the signal recycling mirror. And the sensitivity will be improved by all the upgrades that I told you. For LIGO is more or less the same, in the sense that it's a 2-phase project as well, Advanced LIGO Plus. There is the pre-O4 and the post-O4, what we call phase 1 and phase 2. And they will change something in the infrastructure of the building. They will try to install also some adaptive control of the size of the shape of the beam. They will install as well the same technique of the frequency dependent squeezing to reduce the quantum noise, and they will try to improve the overall optical efficiency in all the system. While for these are the target for 4, while for 5 they have some other technology improvement they would like to introduce, and also for them the target for the global design is to be above 300 megaparsec. You can see in the red curve here the advanced LIGO plus final sensitivity curve target, and it is 325 megaparsec. So also they would like to, we would like to at first almost double our sensitivity, while LIGO in 04 they would like to improve up to, I would say, 200 megaparsec, and then they would like to push hard also to double their current sensitivity. What about Kagra? Kagra, as I said, is just started the operation at the beginning of this year, so they have still to fine tuning their interferometer. So they would like to improve some control strategies. They would like to upgrade the suspension of the mirrors, both at the level of sensor, at the level of software, at the level of control and the hardware, and they would like to improve also their cryogenic system. While for the 05, they would like to change the mirrors, since we know that Kagra mirrors are slightly have a slightly less quality, since the material is different in order to work at cryogenic temperature, and the material that they are using has not as high quality as the silica that we are using in LIGO and Virgo. And this is the target sensitivity of Kagra that is going at least at 25-30 megaparsec for 4, I would say. They would like to reach 25 megaparsec as minimal target, and then all what they can do more than that will be good. Just a few words for the third generation detector. The third generation detector is something that we already started to study right now, and we have 2 different approaches, one in Europe and one in US, and let me say that in our advanced plus detector, we are already starting to study technology that will be implemented in the third generation detector. We have 2 projects. The European one is called Einstein Telescope, and it will be underground, and it will be made by 2 different interferometers. One at low frequency that will work at cryogenic temperature, while another one at high frequency, high power that will work at the room temperature. While the American project is called Cosmic Explorer, and it will be a very huge, let me say, experiment, since the design so far is considering an interferometer with cavities that are 10 times longer than the current one. It means they would like to have an interferometer with a 40 kilometer cavity arm, 40 kilometer long cavity arm. And at the first stage, it will work at room temperature, while for the second stage, they are considering cryogenic temperature. And that's the sensitivity for Einstein Telescope and Cosmic Explorer. We would like to show them in a different way, not in megaparsec, but in redshift. And as you can see, the redshift that we can achieve with the third generation detector, at least on the paper, will be 50 times higher than what we can achieve right now, even more. So that these studies are very interesting, and these are very challenging from the technological point of view. This is the timeline for Einstein Telescope. As you can see, now we are in 2020, so we are starting the design, the technical design in Europe, and we submitted a proposal to the European Union in order to have the first funds needed to build the infrastructure. And in 2024, we will probably decide the site of this experiment. This is just an example. While for Cosmic Explorer, okay, the timeline is more or less the same. It's just probably a little bit delayed with respect to the Einstein Telescope 1, since in Europe we were lucky and we could start slightly earlier the study of the third generation detector. So concluding, I hope that I tried to be quite clear, and I hope that I was able to give you some information about the tremendous science and the very exciting science that we can do with our experiments. And in particular, we were impressed by the tremendous success that we had during the O3 observing run. And for the first time, we were able to observe some particular object, gravitational wave emitted by some particular object in the universe. But we are not happy so far, in the sense that we are pushing hard in order to improve our technologies, our detectors, in order to do even better than what we were able to do so far. And that's all from my side.
Thank you very much. That was really informative. And we've got a handful of questions. Let me jump the line and ask one question. So I've heard that the sensitivity is going to be so great, and you'll be able to hear mergers from so far away that you're going to get multiple signals on top of each other, or you almost get a constant stream of mergers.
Yeah.
Can you say when you think that might happen in the timeline?
Well, I can tell you one particular story. So in O3, for any alert, so we received a call on our mobile phone. I want to ask you to share your video. Okay. So
there you go.
during O3, we received a mobile call, a call on our mobile phone anytime that an alert was sent, in the sense that we have some online pipelines that are analyzing data, and as soon as they find a trigger, they send a call to us, and we have a very short meeting in order to send a circular to the astronomers to, for instance, ask them to point the telescopes in that direction on and that other direction. And already it happened that during one of these calls, I received a second call. It means that we had two events. It was, I don't remember if late in August or beginning of September last year, we received two calls of two events in half an hour. So it already happened with our sensitivity. So can you imagine we improved in sensitivity, but even if the two LIGO detectors will stay like that, well, obviously they would like, we would like that all the detectors will improve the sensitivity, but even if the two LIGO detector will stay with 140, 120 megaparsec of BNS range, and we in Virgo are able to gain some megaparsec in order to be around 100, it will be impressive, it will be amazing, and it will be hell, since I can receive a call every 12 hours or so. So we will have to study also a different approach to handle this. Well, I can tell you that right now the studies of the rate are telling us that for the third generation we will have multiple calls every hour. So we will have to automatize something. If not, it will be impossible to follow it by humans.
Wow, yeah, that's a good problem to have.
Yeah. Yeah.
Let me. We've got a lot of questions here. I'm going to jump to one towards the end by Andrew Thorpe. What efforts are being made to pinpoint the location of the gravitational wave sources?
Yeah. So as I said, the detectors, we have right now 3 detectors. The 3 detectors are in 3 different position on the around the world, and they are also oriented along 3 different direction. It means that for any detector there is a map of the sky, of the universe, and there are some region where the detector are blind, or some region then where they are really sensitive. And what help? It help to increase the number of detector in order to have a better localization, and to increase the sensitivity, obviously. But the most important thing right now is to increase the number of detectors and to have all detectors online. I can give you an example. The first binary neutron star that was detected in 2017, there was a clear signal in LIGO Livingston, a good signal in LIGO Hanford, and no signal at all almost in Virgo. And at the beginning, one can say, okay, Virgo was not enough sensitive and it was useless, etc. But that's not true. The reality, we discovered that the event happened in the region of where Virgo is blind. So it helps a lot in pointing the event. Since we know what is the region of the sky of blindness of all the 3 detectors, and the fact that one of the 3 detectors was blind for that event helped a lot in the localization for this event. And indeed, we were able to have the multi-messengers discovered by telescopes, etc. So the most important thing I would say is to try to improve the duty cycle to have all the detectors online the most of the time.
Okay, I'll go back to the first question. Yeah, Tom Curry was asking, are the silicon mirrors made of specific types of glass, such as Pyrex or?
Yeah, so it's a very good silica, and yeah, I can say that the material should be really homogeneous, and well, I don't remember the exact name of type of silica right now by heart. I'm sorry.
Okay.
But there is only one company in the world that is able to produce this kind of glass with the properties that we want. That is a German company, Areus is called, and they produce the mirror for LIGO and for Virgo. Since we would need a very homogeneous mirror for a very large volume, since you can imagine our mirror have a diameter of about 30-35 centimeter and the thickness of 20 centimeter. So you can imagine the amount of glass, and it should be really homogeneous in all the volume. So it's a very a particular low loss, low mechanics defects, etc.
Okay.
Glass.
All right, and then Henry was asking, what is the motion that's induced by the photon pressure of the mirrors?
Yeah, so on the mirrors, it depends on the amount of light, and it depends also on
I guess it's less than 10 to the minus 18, right?
Yeah, in general, it is less than 10 to the minus 18. Well, what can happen if you increase too much the input power? You have, let me say, too many photons that are hitting the mirrors, and if the mirrors are not well suspended, if the mirror are not well controlled, they can move, and you can see the motion in the sensitivity. We saw it in well, this motion in standard condition is not so high, so it's limiting the sensitivity, but it's not the limit in this range of frequency. But in particular condition, we were able to measure it, and we measure it in around 40 to 60 hertz of our bandwidth, and it was, I guess, if I remember well, 10 to minus 15 meter or so, but more or less. But
Okay.
we made a special experiment since we wanted to measure it, and we were able to measure something of that order of magnitude.
Okay. And are there any problems with natural radioactivity from the materials?
Not so far. No, not so far. We are using passive materials, so for the coating, for the mirror, etc. So we don't have any problem with that. We have problem with the thermal effect on the material, but in the sense that the high power will eat the material, inducing some thermal lenses that we are able to correct, but not radioactivity.
Okay. And then Gabriel has a question about whether or not there's plans for space-based gravitational wave
Yes,
observatory.
there is the so-called LISA experiment that is a space-based experiment. It was already approved by the European Space Agency, and well, the story of this experiment is a bit particular. It started as a European and American combined project between ESA and NASA, but later on NASA decided to jump out, but finally NASA re-jumped in the last years. Fortunately, I'm very happy about that, since it's very important that it will be a worldwide effort. Also, Japanese had their space-based project, but now they are collaborating with LISA as well. So all the world is focused on LISA, and the time scale is as the one of Einstein Telescope and Cosmic Explorer. It means that it should be launched in the space in more or less 15 years from now. And the target of the space-based detector is to detect gravitational wave at lower frequency than the ground base. Since right now I didn't show it, I didn't say that, but the sensitivity of ground-based detector is between 10 hertz and 10 kilohertz for the current detectors. For the third generation, we would like to push down up to 1 hertz, but for the space-based detector, the sensitivity will be of the order of millihertz or even lower. Yeah. So the sensitivity will be in that region of frequency. It means that we can make a very amazing combined science, since they can predict an event that will arrive later on Earth. So that will be really impressive if we will be able to combine our efforts, so we can work together.
Okay, great. Let's see. What's the next one? Oh, yeah. How much power from Reza? How much power do these laboratories consume, and how does it compare to CERN?
I don't know. I'm sorry.
No. Okay, I'm not sure.
I
Okay.
think that CERN. Well, CERN is much larger.
Yeah.
Well, you know, CERN is a sort of town itself. There are thousands of people that are there. while in one of our observatory, either Virgo or LIGO, it's hard to have more than 100 people around per day. Well, in this is a pandemic time, we are 30, 40, no more than that. And I know that in LIGO there were even less. But in standard time, you can have at maximum 100 people around the site. So just that can give you the idea.
Okay. Let's see. And are there tutorials for high school and college students to get hands-on experience on LIGO data analysis?
I would suggest to give a look in the website that I cited before. I can also put the link on the chat right now. If you wait a second.
Okay, sure.
And let me chat. So I think that you can find there all the information about public data, how to analyze data, and etc.
Okay, great. Thank you. Let's see link in chat. And let's see, from Scott Tompkins, does gravitational lensing add uncertainties to the mass estimates, or the mass estimates derive solely from the frequency spectrum and not the intensity of the signal?
Well, I'm not an expert in data analysis. As I said before, I'm more on the instrument side. So I don't want to say something wrong on this.
Okay.
So, but the point is that what I can say is that in general, in a gravitational wave event, you have three different moment of the merging. I mean, you have the inspiral time when the two objects are going one around the other, and they are increasing the speed of that. And then there is the merging time where the two objects are collapsing one into the other. And then there is the ring down time when there is the emission of the gravitational wave, and the final object is becoming stable. And I should say that with the interferometers so far, we are not able to have clear data for all the three moment of the event. So we are able to fit well the inspiral, the merger, but not yet the ring down. And if we wanted to finally estimate in the proper way with less incertitude the total masses, the masses, etc., we should be able to. We have to improve the sensitivity in order to improve our capacity and our knowledge to fit also the ring down moment of the event. So this is a matter of well, it's a data analysis problem, but it's more a matter of the instrument, in the sense that we have to improve the instrument to make this effort easier.
Okay. Let's see, and I think Henry has one question about, could the new object possibly detected via what's the HMNS?
So far we detected BNS, so binary neutron star, BBH, so binary black hole. We have one event that could be BHNS, so black hole neutron star, so a merger emerging between a black hole and another star. But we are looking for new objects as well. We would like to detect sooner or later also gravitational wave emitted by supernovae, and they are emitted around 1 kilohertz in our bandwidth sensitivity. And there is also other gravitational wave that can be emitted by pulsar, and the gravitational wave emitted by pulsar are in the low part of our sensitivity, so around 50, 60, 78 hertz. But so far we never detect something like that. We have to improve a lot the sensitivity there. Right now the sensitivity at low frequency is really limited in all the detectors by technical noises, technical problems. So it's something that we should try to cure. And then there should be also some gravitational waves emitted by the cosmic microwave background, so the background of the universe that were never detected so far. And then who knows if there are also other objects? We don't know. I mean, right now the models and the theory are just giving this one, but well, we don't know if we will discover something new. We hope, I would say.
Okay. Um, I think that does it for the questions. Definitely want to thank you again for taking time to explain this to us. It's very educational, all the sources of the noise and how you mitigate them and plans for the
I hope
future.
that I was clear enough. Well, it's a bit difficult, but well, I tried to do it in the simplest way that I thought. So, well,
Oh, I see there's one common question in the chat. It was from Woody Sims saying he was at the university in Pisa in February, and he met with Professor Steve Shore, and was just wondering if you know Professor Steve
no,
Shore.
I don't know this person.
Yeah, the universities are large. Okay, well, thank you very much, and I look forward to seeing the Virgo LIGA Cagra units improved and results from run 4 when you get them up
Yeah.
and going.
Okay, thank
Okay,
you very much as well. It was a
okay,
pleasure for me.
all right. So this will end the meeting. Thank you, everybody, and enjoy the rest of your morning or day. Thank you. Bye
Thank
bye.
you. Bye bye.